Hi, in this video we're going to be talking about isosceles triangles, a little bit of vocab that goes along with them. Isosceles triangles have legs. They are the two sides that are congruent to each other. They also have a base, and the base is just the side that's not congruent to anybody else. So this thing down here on the bottom, that side is our base. Then we have the base angles. The base angles are the two angles that are opposite these legs. So if we go to the opposite side right here, that's a base angle. This thing right here, those are base angles. They touch the base and they're opposite our legs. So those are our two base angles. And then we also have a third angle inside of there, which is the vertex angle. That's this angle right here. It is what is touching our two legs. So we got two legs, we got a base, we got two base angles, and we got a vertex angle. So what we're going to do down here is we're going to determine the values of x and y in this isosceles triangle that have a common base. Now, what we're also going to see is inside of those isosceles triangles, if these two sides are congruent, that means that these two angles on the bottom have to be congruent. So if legs are congruent, we can say the base angles are congruent. That's true about every isosceles triangle. So if we're looking at this example up here, I can see that these two sides are marked as congruent, and since those two sides are marked as congruent, I know that these two angles have to be congruent. So y has to be the same in both of these spots. With that, we can write a little equation with what we know about all triangles. If you add up all the angles in a triangle, you get 180 degrees. So that means if we solve this, we can say 2y plus 100 degrees equals 180 degrees. We could subtract 100 degrees from both sides. We get 2y equals 80 degrees. Dividing by 2, we can say that the measure of angle y, has got to be 40 degrees. We can use that sort of in reverse over here on this other triangle. Since these two sides are congruent, that means that this angle and this angle have to be congruent. So this has also got to be 50 degrees. If those two base angles are 50 degrees, we could add that to our vertex angle over here, x, and that's going to have to equal 180 degrees. Also, quick solve here. Get 100 degrees plus x equals 180 degrees. Subtract 100. We can say x equals 80 degrees. Well, the measure of angle x has got to be 80 degrees. Cool little solve. Now, cool. What's great about this is it also works in reverse. If you know that the base angles are congruent, that's what's being said in this other diagram. If those base angles are congruent, then we know that these sides have to be congruent. This theorem works in both directions. If you know the base angles are congruent, then you're able to say that the legs are also congruent. So if base angles are congruent, the legs are congruent. If the legs are congruent, then the base angles are congruent. So if I'm looking at this diagram and these congruence statements, it's asking about what's going on with IE. That's got to be congruent to this other side over here that also uses this tick and that single tick. So then IE has got to be congruent to IO because this overall thing is an isosceles triangle. If we look at what's going on with ISL, so ISL, that's this angle right here. This angle has to be congruent to this angle over on the other side. Since these two are congruent, these two have got to be congruent. So this angle over here, ISL, we'll call that ILS. Angle ILS. Done. In this example, a square and a regular hexagon are placed such they have a common side, and we want to figure out the measure of CBH. So CBH is looking for this angle right up top here, and we want to figure out the measure of angle BCH. BCH. So that's this angle that's over there on the side. Now, before we dig into that angle, I want to know some of these other things that are happening with this square and the regular hexagon. Since we got a square, we know that all of these sides have to be congruent. Since this thing is regular, that means that all sides are congruent in the hexagon. That's not true about HC, but it is going to be true about all these sides right here. Now, I already marked this square, so that must mean all of these sides are congruent. So we know HBC is an isosceles triangle. I'm going to redraw that over here just to kind of like help me out. And I'm going to draw it a little funny. I'm not going to draw it exactly like this because then everything's going to be all kind of crammed together. So HBC, I want to figure out the measure of this purple angle. What is that? And I want to figure out the measure of this angle over here. What is that? So I got to get some angles into here. I know there's 360 degrees right here, but if I knew some stuff about what's going on in here, maybe I could figure out how much is left for this purple angle right there. Well, since this is a square, I know that all of these sides are right angles. That's something about it being a square. So I know that's 90. I still got to figure out that part. So if I wanted to figure out the measure of this, I can use this theorem. Each interior angle in a regular polygon is going to follow this measure. So I could figure out this angle B on the outside here by using my little theorem here. This hexagon has got 6 sides, so I got to do 6 minus 2 times 180 divided by 2. This will tell me the measure of the interior angles, or more importantly, the measure of angle ABC. So that's 4 times 180 divided by 2. 4 divided by 2 is 2 times 180. Oh, shoot. This number of sides is 6. That should be a 6 instead of a 2. So let's turn those into 6s. So then instead, let's keep this a 4. Yeah, let's just scribble all that stuff out. So instead, sorry about this, we're going to do 180 divided by 6. That's 30. So 4 times 30 equals 120 degrees. This equals the measure of angle ABC. Great. So I know this is 90. I know this is 120. I still want to figure out the measure of CBH. And I can find that by saying, okay, well, the measure of angle CBH plus the measure of ABC that I just found, that's 120 degrees, plus that right angle that's right here has got to be 90 degrees. And if I add all those up, I should get 360 degrees because this is all going in a circle. So this equals 360. So I can find the measure of CBH by just solving this equation. So let's see, measure of angle CBH plus this is 210 equals 360. So the measure of angle CBH has got to equal 360 minus 210, which is 150 degrees. Hey, that's the first thing that we're looking for. Right there. Cool. So that is 150. Now, since I know that all these sides are congruent. If those sides are congruent, by that isosceles triangle nonsense, I know that that side also has to be congruent. So these two angles have the same measure. I'm just going to call them x for just a little simplified solving. I can say x plus that 150 I just found should equal 180 degrees, and that'll tell me the measure of BCH, because I know that in all triangles, they always add up to 180. So I can say 2x plus 150 equals 180. Subtract that 150. I can say 2x equals 30, not 130, just 30. Divide by 2. X equals 15 degrees, and that x is representing this angle that I was looking for. So the measure of angle, measure of angle BCH has got to equal 15 degrees. All done. So I got this one and that one. All finished. Another theorem we get with isosceles triangles is if we've got these two legs and then we draw a bisector of our vertex. A reminder that our vertex is this angle over on the end here. If we bisect that vertex so that these two are congruent, we get something else about that bisector. And I'm going to draw another little triangle here for that. What this blue line actually does is it forms a right angle to the base, and it cuts that base in half. So we get two equal pieces, and it's going to be at a right angle. So that's what a perpendicular bisector is. It bisects the base, and it's a right angle with the base. Now, we're not going to go into it in this video, but a cool byproduct of this is if a triangle is equilateral. So equilateral means that all of the sides are the same. A triangle is equilateral if and only if. So it's interchangeable with the idea that all of these angles have to be congruent. So if we know this, we know this. And if we know this, we get that, which is kind of nice. Now, some examples that use that perpendicular bisector theorem. Since we've got a bisector here of our vertex, we know that this has got to be a right angle, and we know that these two pieces have to be congruent because here's our vertex, it's being cut in half. That means that our base, this side, has to be meeting at a right angle with this line, and these two pieces have to be congruent. But I should mark them with double ticks because we've already used up single ticks in this diagram. So we're getting a bunch of little pieces of information. We know the measure of angle L is 58 degrees. Well, then the measure of angle LKJ has got to be, let's see, this is 58 and that's 58. This should be the leftover bit. So this is using the idea that those base angles are congruent. 58 plus 58 has got to equal measure of angle LKJ. It's got to equal 180. So if we subtract both of these, from our 180, we get the measure of angle LKJ as a number. We get the measure of that ending up being 64 degrees. If we know JL is 5, so if we know that this whole distance here is 5, then ML has got to be 5 cut in half. So it's got to be 5 divided by 2. So that is 2.5. So that means ML equals 2.5. Easy. If JKM is 48 degrees, then the measure of angle J has got to be what? Well, we're going to double that 48 because I know that this is an angle bisector. So we're going to have to do 48 plus 48 because we've got two of these angles up top. Then the measure of angle J is repeated. So we've got two of those measure of angle J's because these two base angles have to be congruent. And when we add them all up, we should get 180 degrees for this whole triangle that's happening here. So we can say 2 measure of angle J's plus 96 equals 180. Subtracting a 96, we get 2 measure of angle J's equals 84. So if we divide that by 2, the measure of angle J has got to be 42 degrees. I suppose I could have also done that just inside of here and just simplified that a little bit. Angle J plus 48 plus 90 has got to be 180 degrees. You get the same 42. Last one, if the measure of angle J is 55, JKM, let's use that trick this time. So if that's 55, we could say 55 degrees plus 90 degrees plus JKM. That's got to equal 180 degrees. So that is 145 degrees plus the measure of angle JKM. It's got to equal 180. Subtract that 145 from both sides, the measure of JKM. It's got to equal 35 degrees. And that is it for this video on isosceles triangle. A reminder that this is a nice biconditional, that if we know the legs are congruent, the base angles are congruent. If the base angles are congruent, the legs are congruent. And if you bisect that vertex angle at the top of a isosceles triangle, then the bisector is a perpendicular bisector of the base. Thanks for watching. Bye-bye.